So what if we could build a version of the internet where trust isn't just an agreement but an actual mathematical certainty? Well, today we're diving into a really radical paper by Brandon Ramsey that proposes exactly that. It's called the Tripwire Theorem, and believe me, it could fundamentally change how we all interact online.
I mean, this is the big question, right? It's the fundamental challenge of the whole decentralized web. It's the exact same problem that systems like Bitcoin were trying to solve. How do you build a system where people can interact securely without some big central authority like a bank stepping in, and you can guarantee that nobody can cheat?
For a long time, the answer was global consensus, which you see over there on the left. Basically, it means everyone on the network has to agree on a single shared history of everything. And as you can see, that's slow, it's public by default, and it has some real vulnerabilities. But this paper, it proposes a totally new approach called cryptographic stitching. Instead of that slow global agreement, it uses fast, private, and super efficient bilateral agreements. And the real game changer here is that you're moving from a system that's vulnerable to timing attacks to one that has mathematically guaranteed integrity. But, to really get why this new idea is so powerful, we first need to understand the problem it's designed to solve. So let's take a closer look at what we'll call the blockchain bottleneck.
Okay, so here's the core problem with the old way. When every single person on the network has to validate every single transaction, everything just grinds to a halt. It's a massive computational bottleneck. But it's also a security flaw. See, a clever attacker, let's call her Alice for our example, can take advantage of the delay between when she sends a transaction and when it's finally confirmed. She could send the same digital coin to two different people at roughly the same time, creating what's called a race condition, basically hoping that one of her fraudulent payments gets approved before anyone notices the other one.
So, how do we fix this bottleneck and plug that security hole? Well, the paper proposes a solution that's built on 3 core cryptographic tools. You can think of these as the fundamental ingredients for building a system of trust that just doesn't need everyone to agree all the time. First up, we've got the Sparse Merkle Tree, or SMT for short. The best way to think about this is like a highly advanced cryptographic fingerprint. It can take a huge amount of data, like say all of your transaction histories with everyone, and compress it down into a single unique signature. And the real magic here is that you can then prove that something was part of that original giant dataset with incredible speed and efficiency. Next up is the hash chain. Just imagine a digital chain where each new link is literally forged from the cryptographic essence of the link that came before it. So if you try to change or, remove a single link anywhere in that chain, the whole thing visibly breaks. This gives you a perfect, tamper-proof, and ordered record of events. Now this is where it gets really interesting. Instead of having one giant public chain for everybody, this system uses those hash chains to create private, what are called bilateral relationships. It's basically a shared, tamper-proof log of interactions between just you and one other person. This is an absolute game changer for privacy and for scale, and it even makes it possible for transactions to happen completely offline. All right, so we have our tools. We've got the SMT fingerprint and these private relationship chains. So how do we actually stitch them all together to create a secure transaction? Well, this is where something called the atomic receipt comes into play. The core idea is actually pretty elegant. Your device, your phone, your computer, it takes the latest state of all of your separate private relationship chains and then uses a sparse Merkle tree to combine them into one single atomic commitment. This creates that master fingerprint we were talking about. It's like a secure snapshot of your entire world of interactions at a very specific moment in time, all without revealing any of the private details. And this slide lays out the process perfectly. Let's just walk through it real quick. First, Alice proposes an update to Bob. She creates a receipt that proves the link between her old SMT fingerprint and her new one. Step 2, she signs it. 3, Bob gets it, verifies her signature, and checks the cryptographic proof. 4th, if everything looks good, he countersigns it. And finally, they both save this atomic receipt to their private shared log. And that's it. It is now a permanent, mutually agreed upon fact that neither of them can ever deny. It's locked in. Okay, now we get to the heart of this whole thing, the unbreakable tripwire. This is where the system really goes beyond just clever cryptography and becomes this powerful new security model, one that transforms fraud from something you try to prevent into an actual mathematical impossibility. Here's the informal definition right from the paper itself. In simple terms, what this means is that you cannot lie to Bob about your transaction history without creating cryptographic evidence of that lie that will be instantly and permanently detected by Carol or Dave or anyone else you interact with honestly. Your lies are mathematically bound together. You can't tell different stories to different people.
So it's the obvious question, right? What if someone just ignores the rules and tries to double spend anyway? What actually happens in that moment?
Well, the answer is that fraud stops being a game of speed and timing, and it becomes a math problem, a really, really hard math problem. See, to cheat in this system, you are forced to try and create two different SMT fingerprints that both claim to come from the same starting point. This is what's known as finding a hash collision, basically tricking a cryptographic function into giving you the same output for two different inputs. And this is considered computationally impossible with modern cryptography. Honestly, you'd have a better chance of guessing a specific atom in the universe on your first try.
And here it is. This is the tripwire. When you attempt this impossible math problem, you don't just fail. You create permanent, undeniable cryptographic proof of your own fraud. And this proof effectively bricks your device's identity. Any honest participant who sees it will know you're a fraud, and you will be mathematically locked out of the network forever. You can't take it back, you can't undo it. You tripped the wire. Game over.
So let's zoom out for a second. What are the implications of building a system based on this principle? What does it look like when we have mathematically guaranteed integrity instead of that fragile global consensus?
The advantages are huge, and they pretty much directly solve all the problems we saw earlier. You get massive scalability because there's no more global traffic jam. Privacy is baked right in because your history with Bob is completely invisible to Carol. Faults are isolated, so if you have a dispute with one person, it doesn't nuke all your other relationships. You can even transact completely offline, and the whole system is just incredibly efficient. Verifications take a fraction of a second.
If there's one crucial point to take away from all this, it's the paradigm shift. We're moving away from systems that try to make cheating really expensive or difficult through social pressure or economic penalties. Instead, this is a system where the very act of attempting to cheat is mathematically self-destructive.
And that leaves us with a final, pretty provocative thought. Just think about the possibilities. Truly secure voting systems, transparent supply chains, genuinely private messaging, decentralized identity. What could we build if the foundational layer of trust we rely on online wasn't just strong, but was actually mathematically unbreakable? It's a powerful question to think about.